In this video, we are going to derive Euler's identity using Taylor series. This video will be much simpler than my prior videos, but Taylor series for things like e to the ix will appear a lot in my future videos, so I figured I'd go ahead and cover it here. We can go ahead and derive this identity by evaluating the following constant. This is e to the I pi, three very important constants in mathematics. Let's break down what each one of those are. We have pi, approximately 3.1415. We have I, which is exactly the square root of -1. And e, which is approximately 2.7182. This is Euler's number. E to the I pi is approximately 2.7182 to the power of the square root of -1 times 3.1415. We can consider the behavior of the imaginary unit. This will be important. If we know that I equals the square root of -1, squaring a square root, well, those functions undo each other, so I squared is just -1. You'll notice we kind of performed a 90-degree rotation on the complex plane. And it's not just sort of, it turns out that's exactly what we did. So we know what I cubed is. It's just -I. We're now on the bottom part of the plane. And so if we rotate one more time 90 degrees to that right, we will get 1 itself. And so if we take I to the 5th power, we just start over to where we began, and this continues. So I to the 6th power is just -1, I to the 7th power is just -I, so on and so forth. And basically the magnitude of any of these imaginary units from the point 0 is 1. So the magnitude of I to the n equals 1. We are concerned with Euler's number now, denoted by E. There's a famous limit that you can find by just Googling E itself, and this is usually what you'll find. However, we're going to get more intuition here by considering the Taylor series of E itself, just the constant, not e to the x. This is the discrete sum as n goes from 0 to infinity of 1 to the n divided by n factorial. We'll go ahead and expand that so you can see it term for term, at least for the first couple of terms. So we've gone up to the 5th term here. Well, really, I guess you could say the 6th one because we start at 0, not 1. So we get a 1 to the 0th power divided by 0 factorial for our first term. That equals 1. And then we'll get 1 to the 1st power divided by 1 factorial. And then you can see how the pattern continues from there. This is e to the 1st power, so we can go ahead and figure out what e to the x is by just replacing that 1 in the numerator of the Taylor series with x. So far, pretty simple, especially compared to what we've been doing so far. This also allows us to express our series with the imaginary unit, as that will be very relevant to our original problem. We can go through each numerator. For example, I squared is -1, so really that's -x squared over 2 factorial. So if we continue that down the line, we get the following construction. Let's go ahead and look at that one more time here. We'll notice that the imaginary terms are all odd, and now the real terms are all even. And so you can see this pattern, a positive, positive, negative, negative, positive, positive, continuing all the way down. Let's go ahead and factor that. On the left side, we actually have all even terms. I mean, considering, well, you say 1, well, 1 is an odd number. Yes, but that comes from x to the 0th power divided by 0 factorial. And so we have 0, 2, 4 in our numerator for our exponents, and on the right we have 1, 3, 5 continuing. And we continue having that positive, negative, positive now, but split across. So actually what we're looking at on the left side here for 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus so on and so forth It's just a definition of cosine of x. Then we have plus I times what is the definition of sine of x. So therefore, e to the ix, we don't have e to the I pi yet, but we're close. E to the ix is equal to cosine of x plus I sine of x. And this also shows very obviously how cosine is an even function and sine is an odd function. We can trivially evaluate the equation for when x equals pi to bring this around. Well, sine of pi is just equal to 0. I mean, any integer multiple of pi evaluated from sine is going to equal 0. So we're left with cosine of pi plus I times 0. Now an imaginary number multiplied by 0 itself is also equal to 0. So e to the I pi is just equal to cosine of pi. And cosine of pi, quite easily, is just equal to negative 1 radians. And so our argument here is that e to the I pi itself is equal to negative 1. Turns out, this is exactly Euler's identity. And we typically write it as e to the I pi plus 1 equals 0. Finally, we can construct another identity by doubling pi. 2 pi is known as tau. Tau is also an important constant that's more recently been coming up in the discussion. E to the I tau equals cosine of tau plus I sine of tau using our earlier formula. Now, any multiple, as I said, of pi evaluated under sine is going to be 0. So sine of pi, sine of 2 pi, sine of 4 pi, etc. is going to equal 0. And if tau is equal to 2 pi, then sine of tau itself is equal to 0, and I times 0 equals 0, meaning e to the I tau is equal to cosine of tau. Now cosine of tau is different because cosine of pi is equal to negative 1, but cosine of 2 pi flips that to a positive 1. That's the behavior of the cosine function. So now that we know that cosine of tau equals 1, it turns out that e to the I tau is equal to the identity. And that was a little bonus I decided to just kind of throw in there. Thought it was pretty interesting. But really that's all there is to this video. This was a basic mathematical overview of a function that's going to pop up a lot, and more specifically e to the ix, where we have multiple constants and probability parameters and all kinds of things we could be evaluating that at. So this covers up just the generalized basics of it. Hope you enjoyed the video. If you have any questions, feel free to reach out to me in the comments.